All right, we're going to take a look at how derivatives affect the shape of a graph and what this first derivative test can do for us. So first things first, I just want some notation. If f prime of x, so our first derivative, is greater than 0 or positive for all x in this open interval a to b, then we say the function is increasing on a to b. And I think you've known that before, because if we look at something like this, as we look and say, okay, for maybe here on, our slopes of our tangent lines are all positive, and so we have said that that function is increasing. And so on the flip side of that, if my first derivative is less than 0 or negative for all x in open interval ab, then we say that function is decreasing in that interval. Now, if f of x, when I find the derivative, if that derivative is equal to 0, then we say that function is constant because it is actually neither increasing nor decreasing. You are constant. So I'll show you these steps and we'll go through them, but what you're going to basically do is find these critical values that we looked at already. We're going to write these values as intervals on a number line. We're going to pick whatever, sort of relatively easy values we can, and we're going to see what f prime of x is, positive or negative, and then we can make our conclusion. Are we increasing, decreasing, or constant? So I suppose we should add the or 0 there, but hopefully we're only 0 at those boundaries. So first one says find critical numbers, if any, and then we're going to find open intervals on which the function is increasing and decreasing and locate all relative extrema. So it is also important to note that increasing and decreasing have more to do with relative maximum and minimum than their actual placement. So for example, I increase to a max, I decrease to a min. So I would call this down here a relative min or relative minimum, not necessarily just because it's below that relative maximum that I would call up here. Okay, so I'll show you another picture so you can kind of get a sense for what I'm talking about. So this happens sometimes with vertical asymptotes. I might have something that looks like that up here, and I might have something that looks like that down there. This I would call a relative max. This I would call a relative min. And the reason why is because we decrease to a minimum and we increase out. That's the definition of my relative minimum right there. It's not based on location. This is not the absolute minimum, right, which was the absolute lowest in our interval. And those were those y values. These are these turning points, relative or local extrema. So I increase to a max, and then I will see like this one, I decrease out. So that is more important than its physical y value location because I'm not finding the absolute max or min. Okay, so I'm going to find my first derivative and think about these critical numbers. So my first derivative will be 6x squared plus 6x minus 12. Now remember, the first part to critical values was assessing my domain, and my domain for the first one is all reals, so we wrote that two different ways, the double r or the negative infinity to infinity. It's just a third degree polynomial. My f prime is second degree polynomial, so I'm still negative infinity to infinity or all reals. So there are no new restrictions. So there's no additional numbers that I would want to add to my critical numbers list, besides what I'm going to get once I set it equal to 0. So now I will set my first derivative equal to 0. it's important also to note, don't divide by negatives yet. Don't divide by 6. Don't change anything. You're going to need to go back to this f prime level. So you can only start doing that division or factoring things out, things like that, once you equal 0. Leave it alone when it's at the f prime level. So now that it equals 0, if I wanted to divide by 6 to make my numbers a little bit more workable, I could, because then hopefully I can see that I can factor that. So factors of -2 that add to +1. So I have 2 and 1, and I'm going to have +2 and -1. So I have two x values, and at those x values, I have derivatives that are 0. So I have a horizontal tangent line or a turning point that I need to check. So I'm going to go to my number line, and I already cheated because I kind of already made one here, and I'm going to label it f prime of x because I am performing a first derivative test here in this whole problem. When we get to the second derivative test, I'm going to label that f double prime. So for right now, it's f prime of x. And then in numerical order, I'm going to put whatever I found where the x values which made the derivative 0. So the first one was -2, and the second one was a 1. And if you, again, plug those into the first derivative, you should get 0. Okay, so now what I'm going to do is I'm going to look at this as if it's 3 sections. So here's a section of my number line. I can take any x value within that section, -3, -4, -5, -6, doesn't matter. Any x value that's in here that's in the domain of my function, which for me is going to go -infinity to infinity like we talked about. And I can say I'm going to put that number into this first derivative, and all I care about is if it's positive or negative. And we did this a little bit when we studied position, velocity, and acceleration, so this should not be too out of our comfort zone. So if I put in, and again, you do not have to do this by hand, you can certainly do this using your calculator. Let me get that open. Okay, so now I'm going to go to my y equals, and I'm going to choose to use my table. There we go. I'm going to say it's 6 x squared and if I type in that original equation for my derivative, so the 6x squared plus 6x minus 12. So not after you have factored or divided things out, just type in the original derivative, how you have it. And then we're going to go to our table and we type in a value that would be on the left side of -2. So for example, I might type in -3 and I get a positive value. I get positive 24. So that's what I'm going to note on my number line. And so I will go over there to my number line. I will say if I put in -3, I got, what did I get? Positive. Then when I put in something in between, I got negative. So when I put in 0, and then when I put in something greater than 1, I did get a positive. And so I write a couple different things underneath this number line here. That tells me in this section, for all these x values, my first derivative is positive, which means it is increasing as my function, meaning is increasing, or it looks like so. And then in between -2 and 1, my function, again, it's talking about my original function, is decreasing, because remember our derivative is really nothing more than a descriptor or adjective of our original function. And then everything greater than 1, when we put that into our derivative, we got a positive value. Okay, so what I'd like to talk about right now. Okay, so then I would be increasing here. And so now I can answer the question, and I'm going to put a couple more things on here, but I can answer the question for sure of when I'm increasing and when I'm decreasing. But what I also would like to note on here is that you increase, then you turn around and decrease. So this -2 comma something is going to be a relative maximum. Again, not necessarily based on the y value or the position of the point, just based on what type of turning point it is. Then the 1 is going to be called 1 something is a relative minimum because you are decreasing to that minimum and then increasing out. So I can say I'm increasing. These are all interval notation. Okay, x values. So I'm increasing in this first highlighted section here, and then in this section right there. And so I'm increasing from -infinity to -2. And then I'm also increasing in the other blue highlighted section on that number line, which was from x equals 1 to infinity. And although x equals 1 is included on my original curve, again, we don't want to include that in where our first derivative is increasing, because technically at 1 then you could ask yourself, well, are you increasing or decreasing? Because it's kind of seen in both, because again, the in between here is where I'm decreasing, and so that's going to be between -2 and 1. And I'm not decreasing at the same time that I'm increasing. And so because our definition of decrease and increase is based on 1 point now, because we are talking about an instantaneous rate of change, I am neither positive nor negative at that one specific value, so we just say we're constant there. And so we do not include any values in our increasing and decreasing intervals. And so then I'm decreasing in between, which was the -2 to 1. Now, relative max as a point is going to be -2 comma something. Again, if they're asking for a maximum value, they're probably asking for that y value, but I'm okay if you give me the point, and again, that's a personal preference, but if they're asking for a relative minimum value or relative maximum value, those types of values can sometimes be y values. They can also ask you at what x value does the relative max occur. In that case, you already have that answer, x equals -2. So in order to find where the relative max is at a point, or in order to find that y value, you do have to go back to the original function and put -2 in and evaluate that. So I'll just show that by hand real quick. So I'm going to do f of -2, and it's 2 times -8 plus 3 times 4 plus 24. So -16 plus 36. So I do get 20. And then the relative minimum, I will evaluate f of 1. Again, this is on the original curve. So it's 2 plus 3 minus 12. So -7. And so, yes, in this case, relative minimum did occur to be lower than my relative maximum, but that is not an always situation. Okay, and I'll use Desmos right now to check this so you can kind of see a different graphing tool. If I put the original function into Desmos, again, I'm checking the original function here. 2x cubed plus 3x squared minus 12x. Okay. And I'm going to change the window so I can see what I'm looking for here. Maybe I'll zoom out a little bit. Now, what we were suggesting is that when I looked over here, we said that we were increasing from -infinity to an x value of -2. And you can see that for sure I'm increasing -infinity to this x value right here, which does appear to be negative 2. Then between negative 2 and x equals 1, I am decreasing. Then you can see from 1 to infinity, forever, all these x values, you are increasing again. So I can use my first derivative, again, to describe that original function. I hope you found this helpful to get started with increasing, decreasing, and relative max or min.